In Chapter 7, we will talk about solving systems. So why do we want to solve systems? When we solve equations, we only have one unknown variable that we want to solve for. Solving a system allows us to solve for two variables that are dependent on each other. If we get larger systems, we could solve systems of equations for 3 variables that are dependent on each other, or even more. There are many real-world applications which we will see some of during some of our story problems that we will look at as we continue throughout this chapter. Now there's 3 main methods for solving systems of equations. The first one is the most basic, and it is by graphing. The second one, a lot of you are probably familiar with, but we'll still go over it in detail, is substitution. And then the final one is the elimination method. The elimination method is also sometimes referred to as the addition method. All right, first off, solving by graphing. This method actually does not work well in most cases, but we will see a few cases where it does work nicely so that we can practice it. To do this method, we will graph both equations and look for an intersection point. On this, we run into problems when the intersection point is not a nice point, so we can't tell for certain what that point is. Then we won't be able to find the solution. So solving by graphing will work in a few cases, but it's not perfect. Solving by substitution, on the other hand, this method always works, and it always works nicely. The first thing that you will do is you will solve one equation for one of the variables. Then you will substitute what you found in step 1 into the other equation, and this will give you an equation with only one variable. At this point, you're able to solve the equation that you made in step 2, and then you substitute this solution into one of our original equations, and that will allow you to solve for your other variable. Now you're always going to answer as an ordered pair or for a story problem with words. Remember, you're often going to be solving for x and y, so your x would go first and your y second. So again, our steps: solve one equation for one of the variables, substitute what you found there into the other equation so that you have an equation in only one variable, solve that equation, then substitute that solution back into one of your original equations to solve for your other variable, and then answer as an ordered pair, or in the case of a story problem, with words. Next, there's solving by elimination. This method also always works. This method a lot of people find to be a little bit trickier at first, but with some practice, you might find that you prefer this method. The first thing that you will do for this method is you'll write both equations with x and y variables on the left side of the equal sign and the constants on the right side of the equal sign. We want to write one equation above the other equation, lining up our corresponding variables. So the x's above and below x's, y's lining up, and then our constants lining up on the other side of the equal sign. Step 3 is the tricky part. You determine what non-zero constant or constants that one or both equations will need to be multiplied by, so that the sum of the equations will result in an equation in just one variable. Once you've found that, you multiply it in and then add the two equations together to get an equation in just one variable. So you'll have just one equation now, it's in just one variable. So you're going to solve that equation. Once you solve that equation, you now have a solution for one of your variables. So substitute that value into one of your original equations and solve for the second variable. Again, we're going to answer as an ordered pair x, y, or for story problems, you'll answer with words. So again, your steps there, you're writing both equations so that x and y's are on one side of the equal sign, constants on the other side of the equal sign. And you're writing them one above the other, so your x's are lining up, y's are lining up, equal signs line up, and your constants line up on the right-hand side. Then you're determining that non-zero constant or constants that one or both of the equations should be multiplied by, so that the sum of the equations will result in an equation with just one variable. Here you're really thinking, I want to get this so that my x's when added together gives me 0x, or my y's when added together gives me 0y. That's what you're thinking as you're doing step 3. Step 4, you're just adding those equations together once you've multiplied in that constant or constants, and that gives you an equation in one variable for which you can solve. So you solve that equation to get a solution for one of your two variables. You then substitute that value into your original equation and solve for the second variable. You answer as an ordered pair x, y, or again for story problems, you'll answer with words. Let's look at some examples. First, let's solve by graphing. Here is a system of equations, and of course if we're going to graph, we should have a coordinate plane to graph on. Now when we're trying to graph, it might be best if we had both of our equations in our slope-intercept form, because that's our nicest form for when we try to graph. So slope-intercept form is when we have solved for y, we have y equals mx plus b. Our first equation is in that form already. The second one we need to solve for y. Take a moment, go ahead and try to solve for y, pause if you need to. And here we have our second equation solved for y. So now both of our equations are in slope-intercept form, so we should be able to graph both of them. When we graph that first equation, we use our y-intercept of -1, slope of +2. We get our 2 points, draw a straight line between them. And for our second one, we use our y-intercept of 2, slope of 1/2. That gives us 2 points, draw a straight line in between them. Now we look for the point of intersection. What point do these two lines share? They share the point 2, 3. So the x value of 2, the y value of 3. So that was solving by graphing. Let's try solving by substitution. Let's look at this example here. In this example, we have x plus y equals 28 for one of our equations, and the other equation is y equals 3x. We're told here to solve by substitution, so what we want to do first is solve one of the two equations for one of the variables. Notice that second equation is already solved for y, so our first step is actually done for us here already. So since we have our second equation solved for y, we're going to substitute what we know y equals into our first equation. So instead of our first equation reading x plus y, it'll read x plus 3x equals 28. So again, instead of y in that first equation, we are writing 3x. Now we just need to simplify. So simplify your left-hand side. We have 4x equals 28. Solve for x by dividing 4 on each side. We have x equals 7. Well, now that just gives us a solution for x. We need a solution for x and y both. So we're going to plug this back into either of our original equations. I'm going to use that second one. So I know y should equal 3 times x. I know that x equals 7. So I'm saying y equals 3 times 7. 3 times 7 is 21. Therefore, y equals 21. This gives me a solution, an ordered pair, of 7, 21. Now let's try an example by elimination. So we're going to solve this system here by elimination, and remember that this method is sometimes also called the addition method. So if I want to solve this by elimination, I am going to make sure that I first and foremost have both equations written so that I have x, then y, my equal sign, and my constant on the right. And both equations are sitting there in that form, so that's nice for me here. Next, I want to determine which variable that I want to get rid of and think about what constant or constants I might need to multiply by in order to make that happen. I'm going to try to get rid of x. So I want to think of what should I multiply one of my x's by, and hence the entire equation. So we have to do everything by equation. What do I want to multiply an x by so that when I add my x's together, I'll get 0x? Well, if I multiplied that first equation by 2, I would have 2x. The second equation has negative 2x. So then adding them together, I would have 0x. I would eliminate an x. And so that's what I'm going to do. I'm going to multiply that first equation by 2. So multiplying the first equation by 2, we're multiplying on both sides of the equal sign. So make sure you distribute the 2 all the way through. Your first equation should now read 2x minus 8y equals 38. Your second equation has not changed. It is still negative 2x plus y equals 11. Now what we're going to do is we're going to go ahead and add these two equations together. So add your x's together, add your y's together, add your constants on the other side of the equal sign together. So our x's are going to eliminate here, and our y's, we're going to end up with negative 7y, and our constants on the other side, we have 49. So we have negative 7y equals 49. Then solving for y, we want to divide both sides by negative 7, and we will find that y equals negative 7. Now we have a solution for y, but we still do not know x, so we're going to take this solution for y and plug it back into one of our original equations in order to find x. I'm going to plug it into our first equation, and so I have x minus 4 times negative 7, because that's my solution for y, equals 19. Now I'm going to start to simplify, so negative 4 times negative 7 is a positive 28, so we have x plus 28 equals 19. Now subtract 28 from both sides, x equals negative 9. Now we need to answer as an ordered pair since we have a solution for x and a solution for y. Our ordered pair would be negative 9, comma negative 7. And this is solving by elimination. So that's told you how to work with systems of equations, but we will also work with systems of inequalities. So in order to work with a system of inequality, we're always going to solve by graphing. So those of you who enjoy graphing, this is going to sound like a good thing for you. So our answer is actually going to be the graph itself. So we don't have to read anything from the graph, we just have to be able to graph everything appropriately. So the first thing that we want to do is graph each equation using a solid line for a non-strict inequality or a dashed line for the strict inequality. These are what we're going to call our boundary lines. We will then choose a test point and determine if it is a solution. If it is, then we'll shade that area and we continue until we have just one shaded area. So let's look at an example here. Here's a system of inequalities. We see that both of these are strict inequalities, so we will be using dashed lines for each of these as we graph. And sometimes it's helpful to graph first, sometimes it's helpful to choose a test point first. Here I'm going to choose a test point before I graph my lines, just because when graphing on the computer it's a little bit trickier. When graphing on the computer, you'll graph your line, then you immediately have to select a test point and graph shade one of the sides. So I'm going to choose the test point 0, 0. When I choose my test point, I want to make sure that my test point is not on either of my lines. 0, 0 often will work well for you. You just want to make sure that 0, 0 is not on one of your boundary lines when you use it. So you're going to look at the test point 0, 0. You're going to ask yourself, does this point make my inequality true? So first, looking at your first inequality, does that make it true? So plugging it in, 0 less than 2 times 0 plus 2. That'd be 0 is less than 2, which is true. That's yes. So what I'm going to do, I'm going to graph that first boundary line using a dashed line there. And then I'm selecting my test point because that was a solution. Now, if I had found it was not a solution, I could have just selected a point on the other side of the line because it's either on one side or it's on the other side. And we will see some examples where when we choose a test point, we find that no, that test point is not part of my solution, and we'll see how to handle it then. So using the test point 0, 0 again with our other inequality, we see that this one also is true. So 0 is greater than negative 0 minus 1. So 0 is greater than negative 1. That's true. So we are going to graph our other line, select our test point again because that was a solution. And this is the graph of our solution. Now, solutions for the system occur where the overlap is. So the overlap is our answer. But on the computer, we're just going to leave our graph like this. Just remember that the overlap is your answer. Let's go ahead and look at another example. We're going to look at an example here where we may not have straight lines for all of our inequalities, and that's okay. We know how to graph some parabolas, so I might throw some parabolas in there for you to work with. Again, I'm going to choose the test point 0, 0. 0, 0 is not on the boundary line for either of these. And remember that boundary line is found by thinking about our inequality as having an equal sign in there instead of our inequality symbol. So looking at our first inequality, y less than or equal to 4x squared minus 1, we're asking ourselves, when we plug in 0, 0, does that make this true? Yes or no? So looking at this, plugging in 0, 0, we have 0 less than or equal to 4 times 0 squared minus 1. So that would be saying 0 is less than or equal to negative 1. No, that is not true. So this is our first case where we're seeing that our test point is not part of the solution. So we're going to graph our boundary line. So graphing this boundary line, we would see our vertex is 0, negative 1. And then one other point that we could have along this line, plugging in 1, we could see that we would have 1, 3 as another point. So we could graph our parabola then. And then instead of selecting the test point 0, 0, since we said that's not part of the solution, we just select something that's on the other side of our line. So here I selected the point 0, negative 2 to tell it to shade on this other side of the line. Now, let's look at our second inequality here, and we have a test point of 0, 0 again. Plugging in 0, 0, we find that it is in fact true. And so we will graph our line. This is a line here, a y-intercept of 2. A slope of negative 1 over 2. And we can go ahead and use our test point as our point to plot. And we see that our overlap happens both below the parabola and below our dashed straight line. Remember, the overlap is your solution here. All right, so we've covered systems a little bit, but there's a few other ways that we can work with systems, and I'm sure some of you are getting tired of the alphabet being in your math. So we're going to solve systems using matrices. It's actually our fourth method for solving systems that I didn't mention earlier because it involves us thinking about matrices a little bit first. So we're going to talk about matrices for just a little bit, and then we will talk about solving systems by using matrices, and then get into some story problems. So some matrix math that we will do, we can add and subtract matrices. We can multiply matrices by a scalar, and I'll define what that is in a little bit. We can multiply two matrices together. We'll have to be careful as we do that though. And then we can get matrices into row-reduced echelon form. That's RREF for an abbreviation. And then we will find matrix inverses. Now there's two ways that we could use matrices to solve systems. One involves using row-reduced echelon form, and one involves using matrix inverses. We're going to use the row-reduced echelon form and not the matrix inverse one, but you can definitely look some information up online if you wanted to about using matrix inverses to solve systems of equations. We're going to go through this list and we're going to learn how to do each of these things. So let's start with adding and subtracting matrices. To add or subtract matrices, you will add or subtract elements in like position. So say we had a 2 by 2 matrix and we were adding to another 2 by 2 matrix. Our matrices will have to be the same size of matrices in order for us to do this. So our matrices, if I said it was a 2 by 2, that means there are 2 rows and 2 columns. We always talk about rows first, then columns. Nice way to remember this is R, then C, kind of like RC cola. That's just my fun little way of remembering it. So we're adding things in like positions. So my first row, first column, plus first row, first column gives me my answer, first row, first column. So A plus E is my first entry, and then B plus F, C plus G, D plus H. If I was subtracting, I would do a very similar thing, subtracting elements in like position. Remember, you have to have matrices that are the same size in order for you to add them or subtract them. Multiplying a matrix by a scalar goes pretty quickly as well. To multiply by a scalar, we're going to multiply each element by the scalar. So if we had some number sitting out front times a matrix, we're going to multiply each position in the matrix by that scalar. So if I had S times my 2 by 2 matrix A, B, C, D, we would have in the first position SA, then next we would have SB, then in our second row we have SC, and then SD. We'll replace these letters with numbers in just a minute, and you'll see how it works really easily with some examples. First, though, let's talk about multiplying matrices. Now, we have to be careful when we go to multiply matrices together. You can only multiply matrix A times matrix B if the number of columns in matrix A equals the number of rows in matrix B. Now, our result will have the same number of rows as matrix A and the same number of columns as matrix B. For position AB in the answer matrix, we will multiply position-wise from the 8th row and the bth column. Then we find the sum of these products. So, for example, looking at a little 2 by 2 matrix, multiplying these together, for my row 1, column 1 position, I am going to use my row 1 from my first matrix, and then my column 1 from my second matrix. So I'll take A times E and B times G. Then I will add these together. So I'm using row 1 and I'm using column 1. Now, for my row 1, column 2 element, I will use row 1 again from my first matrix, and then I will use column 2 from my second matrix. So I have A times F, and I have B times H, and I'm going to add them together. And then when I start working with row 2, my row 2, column 1 item, I will use row 2 from my first matrix, column 1 from my second matrix, multiplying piecewise together and then adding things together. And I continue that for the problem. All right, I think it's a good time to look at some examples, so let's do that now. Let's try to add a couple matrices together. Now remember, we're going to add in piecewise, position-wise ways. So I would take -5 plus 0, because both of them are in my first row, first column. And then I'd have -1 plus -1, because both of those are in my first row, second column. And then I'd continue the same thing in my second row, 0 plus 4, and then -3 plus -3. I could also subtract matrices. So I could subtract these two matrices. Again, I'm going to subtract position-wise, so -5 minus 0, -1 minus -1, 0 minus -4, and -3 minus -3, giving me -5, 0, -4, 0, reading them going row by row, going left to right. Well, since we can add and subtract without a problem, let's try to multiply the matrix by a scalar. And we'll work with a bigger matrix here. This matrix is a 3 by 3 matrix. There are 3 rows and there are 3 columns. Remember, your rows are going horizontal, your columns are going vertical. So multiplying this matrix by a scalar, I'm taking every single piece inside my matrix and I'm multiplying it by 6. So 6 times 2, 6 times 1, 6 times 0. That will give me my first row. 6 times -1, 6 times 5, 6 times -2 gives me my second row. 6 times -5, 6 times 8, 6 times -7, that gives me my third and final row. All right, multiplying two matrices together. This was the trickier one. And I've got a fairly nice sized example here for us to look at. And we're going to take our time as we go through this. So multiplying these two together, we first want to think to ourselves, do these, in fact, work to multiply together? In order to multiply them together, we need to ask ourselves, is the number of columns in my first matrix equal to the number of rows in my second matrix? Well, to answer that question, my first matrix is a 2 by 3. There's 2 rows, 3 columns. And my second matrix is a 3 by 4. 3 rows, 4 columns. So it's nice when we see them, the size of our matrices sitting next to each other. We see that 3 and 3, those are equal. And this also tells me the size of my answer matrix. My answer matrix is going to be a 2 by 4. So now in order to figure out my solution, what I need to do is take and multiply things together carefully. So what I'm going to do is for my first row, first column for my answer, I am going to use the first row in my first matrix and my first column in my second matrix. I'm going to go ahead and throw up all the math here so that you can follow along with as we talk through each part. But I'm taking my first row, 7, 5, and 8, and I'm multiplying it position-wise with the first column, -10, -7, -1. So I'm taking 7 times -10, 5 times -7, and 8 times -1. I'm going to add all of those together, and that would give me my answer for that first position. So when we add them together, we'd have negative 113. Now let's talk through a couple more of these parts here, and then I'll let you work through it on your own to make sure that you're understanding it. So go ahead and take the time to pause the video, work through it a little bit, and make sure that you're understanding. If you're not understanding, do make sure that you email me and we can work through it together a little bit more and make sure that you understand how to work these problems. So let's continue working in our first row. I'm going to do another one in the first row, then I'll do one in the second row. So let's do my first row, second column. So first row, second column means I'm going to use a first row and I'm going to use the second column. So I'm going to use the row 7, 5, 8 and the column 3, 0, negative 4. So I will take 7 times 3, 5 times 0, 8 times negative 4, and add all of those together, and I'll get negative 11. So again, I was using the first row, second column. That gave me the answer that went in the first row, second column position. So let's try to find the answer for the second row, fourth column position. This would be our very last one, that answer of 21 sitting down in our bottom right corner. So that's our second row, fourth column. So we're going to use the second row in our first matrix and the fourth column in our second matrix. So we're using the row 9, 1, negative 7, that's our second row, and the column negative 2, 4, negative 5. That's our fourth column. So 9 times negative 2 plus 1 times 4 plus negative 7 times negative 5. Putting all of that together, we do get 21. So again, take the time to pause and make sure you're understanding how to multiply matrices correctly. If you have any further questions, make sure that you do email me so that I can answer those questions. We're now ready to talk about row-reduced echelon form, abbreviated as RREF. Now this form is fairly similar to the elimination method, so I will caution you to make sure that you're understanding the elimination method fairly well before you start working with your row-reduced echelon form. So if you need to pause the video here, go work with your elimination method for a little while, practice with it, and then come back to the video and continue to watch and practice using the row-reduced echelon form after that. That might be a good idea. But so row-reduced echelon form, the first thing we're going to do is we're going to multiply the first row by something, some constant, to make the first element of the first row equal to 1. Then what we're going to do is we're going to add multiples of the first row to other rows so that all other elements in the first column are equal to 0. Then we repeat this until all the columns are 1s and 0s, with 1s along the diagonal, except for the last column. So we're going to work column by column, first getting a 1 in the correct position, and then making everything else 0s. We have to start with the first column first, making that first thing into a 1. You might have to multiply by a fraction in order to do this, but you always want to make that a 1 to begin with. Then once that's a 1, you're going to add multiples of that row to the other rows so that those other elements in that first column are equal to 0. And we're going to go through an example now of getting a matrix into row-reduced echelon form. So we are going to start with the matrix, a 2 by 3 matrix, where the first row is 3, 6, 9, and the second row is 4, 5, 7. We want to get that 3 in our first row, first column, to become a 1. To get that to become a 1, we would have to multiply by 1/3. So we're going to multiply the entire first row by 1/3. We kind of treat our rows like equations. If we do something to one thing in the row, we have to do that same thing to the entire row. So because we want that 3 to be a 1, we have to multiply the entire row by 1/3. So once we multiply that first row by 1/3, our first row now becomes 1, 6/3, 9/3, which is just 1, 2, 3 once we simplify. Now notice that our second row has stayed the same this entire time because we're only messing with our first row right now. Now, once we have our matrix so that we have 1, 2, 3 in our first row, 4, 5, 7 in our second row, we see that our goal of getting the first item in our first column to be in a 1 has been accomplished. Now what we want to do is we want to make everything else in our first column to be a 0, which means that 4 needs to be a 0. So now I want you to ask yourself, what would we have to add to 4 to make it 0? Well, the thing that we would add to 4 to make it 0 is -4. So we're going to think to ourselves, okay, I'm going to multiply in my head my first row by -4, and then I'm going to add that to my second row. Now to help us out as we're thinking about multiplying row 1 by -4, sometimes it's useful to write in with a different color what row 1 times -4 would be. So I'm going to write it right next to row 2 since I'm going to add it to row 2. But as you can see here, row 1 times -4 would be -4, -8, -12. And I'm adding that with row 2. So 4 plus -4 is 0, 5 plus -8 is -3, 7 plus -12 is -5. So again, that's written in red. That's what I get when I take my row 1 times -4. And then I'm adding that there in red to my row 2. Now once we've done this, we see that my first column here has a 1 and then zeros for the rest. So now I want to work with my second column. And when working with my second column, I want my second item, my second row. So second column, second row, that now needs to be a 1. So we're going to ask ourselves, second row, second column, second row, what is that? That's -3. How do we make that into a 1? And when we make something into a 1, we're always asking, what do I multiply by to make this a 1? Well, the answer is going to be we have to multiply by -1/3. So we're taking our second row, so that's where we're changing something in, and we're multiplying that by -1/3. So multiplying my second row by -1/3, I have 0, 1, and then 5/3. So in my second column, I have the 1 where I want it. It's in my second row. So second column, second row needs to be a 1. And now I need to make everything else become zeros in that second column. So now I'm asking myself, how do I make that 2 that is in my first row, second column, become a 0? When we're trying to make something a 0, we're asking, what do I add to this number to make it 0? So what do I add to 2 to make it 0? Well, I would add a -2. Well, I can't just add -2 to everything there. I need to multiply that second row where my 1 is by -2, and then add it to the first row. So it's like I'm multiplying that bottom row, my second row, by -2, then adding it to row 1. So multiplying that bottom row by -2, I would have 0, -2, -10/3. And I've written it there in red for you. And then we're going to add it with row 1. And so I wrote it right next to row 1 so we can see what we're adding to nicely. So 0 and 1 makes 1, negative 2 and 2 makes 0, negative 10/3 plus 3 makes negative 1/3. And now we have this in row reduced echelon form because we have 1s along our diagonal, 0s other places, and then if there's columns off to the right that we haven't messed with, that's okay because we don't have any more diagonal to work with. But so this is in our row reduced echelon form. We're going to see in a little while how this relates to our equations that we've been solving. First, though, we are going to talk about matrix inverses. So to find the inverse of a matrix A, we will augment matrix A with the identity matrix I, and we will get it into row reduced echelon form. And that will give us the inverse of A on the right side of the augmented matrix. So we're going to take matrix A, and here I've shown a 3 by 3 matrix. We're going to augment it with the identity matrix. The identity matrix has 1s along the diagonals, 0s everywhere else, and it's a square matrix. And then we're going to put it in row reduced echelon form, which means that we'll have that identity there on the left-hand side then. So 1s along the diagonal, 0s other places. And then those 3 columns there on the right then would be the inverse of A. So that means we get more practice with our row reduced echelon form. Alright, so our next example has us finding the inverse of the matrix A. We are going to work with a 3 by 3 matrix here. And by the way, you're going to be working with square matrices when you're trying to find inverses. So they'll have the same number of rows as they do columns. So we're going to take our matrix A and we're going to augment it with the identity matrix. So remember, the identity matrix has 1s going along the diagonals and 0s everywhere else. So when we augment matrix A with the identity matrix, this is what we will end up with. Now, I have not included the thorough steps with putting into row reduced echelon form that I had on our previous example, but I will audibly explain what we are doing each step of the way. So once we've augmented our matrix A with our identity matrix, we need to get this into row reduced echelon form. So we're going to look at our first column, first row, and we're going to say we want this to be a positive 1. Currently we have negative 1. To make this into a positive 1, we would need to multiply that first row by negative 1. So we're multiplying row 1 by negative 1 here. And multiplying row 1 by negative 1, our first row becomes 1, 0, 1, negative 1, 0, 0. Our other 2 rows remain the same. Our next step is going to be to get the other items in that first column to become 0s. So next we're looking at our first column, second row, and we're saying negative 1. What would I add to negative 1 to make it 0? Because whenever we try to make something 0, we're trying to say, what do I add to this to make it 0? So what do I add to make negative 1 0? Well, I would add 1. So I'm going to use 1 times my row 1 and then add that to row 2. So my row 2 is what changes. And I will now have a row 2 of 0, 1, 0, negative 1, 1, 0. My first row and my third row have remained the same. Next, we're going to try to get that third row first column element to become a 0. That element right now is a 4. To make that a 0, we ask, what do I add to 4 to make it 0? Well, I add negative 4. So we're going to, in our head, do negative 4 times my first row. Then we're going to add that to my third row. So negative 4 times 1 is negative 4. Add that to 4. We'll get 0. Negative 4 times 0. Add that to 1. We get 1. Negative 4 times 1. Add that to 3. We get negative 1. Negative 4 times negative 1. Add that to 0. We get 4. Negative 4 times 0. Add that to 0. We get 0. Negative 4 times 0. Add that to 1. We get 1. So that's how we get our third row there. Now, my first column is in tip-top shape. I have a 1 in my first row and then zeros for the rest of that first column. So now I'm going to look at my second column. I always go column by column. So I'm going to look at my second column. And in my second column, the second thing down, so in my second row, second column, I want that to be a 1. Well, right now it's a 1, so I'm looking good. That gives me less work that I have to do. That's nice. Now I want everything else in column 2 to become a 0. I see that in column 2, my first row element is already a 0. So I just need to work in column 2 with that third row element. It's currently a 1. I want it to become a 0. Well, if I want a 1 to become a 0, I ask, what do I add to make this a 0? What do I add to make 1 a 0? Well, I add negative 1. So I'm going to do negative 1 times row 2, because that's where my 1 that I wanted to have there is. And I'm going to add that to row 3. So I'm going to do negative 1 times 0 plus 0. Negative 1 times 1 plus 1. Negative 1 times 0 plus negative 1. Negative 1 times negative 1 plus 4. Negative 1 times 1 plus 0. Negative 1 times 0 plus 1. And that gives me my third row, which now reads 0, 0, negative 1, 5, negative 1, positive 1. Now my first column is taken care of and my second column is taken care of. So I will move into my third column now. In my third column, I want the third row to be a positive 1. When I'm trying to make something into a positive 1, I'm asking, what do I multiply by to make this a positive 1? Well, right now I have negative 1. To make negative 1 into a positive 1, I would multiply by negative 1. So I'm going to multiply the entire last row, my third row, by negative 1. So my third row now is 0, 0, 1, negative 5, 1, negative 1. Now I want everything else in that third column to be a 0. My second row already has a 0 there, so I'm just working with that first row. I need to make that 1 into a 0. So I'm asking myself now, how do I make 1 into a 0? I'm making something into a 0, so I'm talking about adding. What do I add to 1 to make it negative 1? I said that wrong. What do I add to 1 to make it 0? I add negative 1. So that's what I'm going to do. I'm going to multiply my third row by negative 1 and add it to my first row. So I'm doing negative 1 times 0 plus 1 gives me 1. Negative 1 times 0 plus 0 gives me 0. Negative 1 times 1 plus 1 gives me 0. Negative 1 times negative 5 plus negative 1, that gives me 4. Negative 1 times 1 plus 0, that gives me negative 1. And negative 1 times negative 1 plus 0, that gives me 1. Now at this point, we see that we have the identity matrix there on the left-hand side. My first 3 columns are the identity matrix. That means the next 3 columns make up the inverse of A. So the inverse of A then is 4, negative 1, 1 for my first row, negative 1, 1, 0 for my second row, and negative 5, 1, negative 1 for my third row. And that is the inverse matrix. So how am I going to use this to help me solve a matrix, solve a system with a matrix. So to solve our system by using a matrix, we're going to use row-reduced echelon form. We're going to get our system so variables are on the left-hand side of the equal sign and constants are on the right side. We will put our system into an augmented matrix. So basically each column is going to be for a different variable, and our final column is going to be for our constants that are on the right-hand side of the equal sign. So each row is representing an equation, each column represents a variable, with that last column being the constants. Then we're going to get this into row-reduced echelon form. The last column has our answers. So let's look at an example here real quick. Solve the system using a matrix. We're given the system where we have 3 equations with 3 unknowns. We're trying to solve for x, y, and z. And whenever I have 3 unknowns, I tend to use matrices to solve because it works a little bit smoother in my opinion, but you can use whatever method you want to when you are solving these. Now, trying to change this system into a matrix, my first equation is going to be my first row. My second equation will be my second row. My third equation will be my third row. As we're looking at this, we want to make sure that if a variable is missing from an equation, we use 0 in the matrix to say that we had 0 x's or maybe 0 y's or 0 z's. So, as we look at this, all of our equations have the variables on the left-hand side of the equal sign and the constants on the right-hand side of the equal sign. So we're ready to put this into a matrix. My first row, I will have 1, 1, negative 1, 250, because those are my coefficients and my constant. My second row will have 0, negative 3, 5, 100, because those are my coefficients and then the constant. And then the third row will have 0, negative 11, 18, and 200. Again, because those are the coefficients and the constant that is on the right-hand side of the equal sign. Now we're going to try to get this into row-reduced echelon form. My first column's already looking pretty good, so I'm going to move to my second column. My second column, I need that negative 3 to become a 1. So I'm going to multiply everything in that row, my second row, by a negative 1/3. So you'll notice that my first row and my third row did not change. My second row is the only one that changed here. Now that I have a 1 in my second row, second column, I'm going to make the other things in that second column become zeros. So to make a 1 a 0, I would need to add negative 1. To make a negative 11 0, I would need to add 11. And I did both of those in one step there. Go ahead and pause, take your time, work through it, make sure that you're understanding how we came up with each of those values there. And do remember, you can always email me with any questions that you have. So our second row, our second column is now in good shape. So our first column, second column, both looking good. So now we need to look at that third column. Our third row needs to have a 1 there. So that negative 1/3 down there needs to be a positive 1. When we're trying to make things into ones, we multiply. So what would I multiply negative 1/3 by to make it 1? Well, I'd multiply by negative 3. So I'm going to multiply that last row by negative 3. My first 2 rows stayed the same here. Just multiplied that last row, everything in the row, by negative 3. Now what I'm going to do is I'm going to try to make everything else in column 3 become a 0. So I need to, for my first row, I would add a negative 2/3, and for my second row, I would need to add a positive 5/3. So when we do that, we're going to end up with my first row being 1, 0, 0, negative 50. My second row is 0, 1, 0, 800. And my third row is 0, 0, 1, 500. Now, this final column has all of our solutions. Our solution for x is -50, our solution for y is 800, and our solution for z is 500. We could put that as an ordered triplet, x, y, then z. And notice that if we tried to change our matrix back to equations, we'd be saying that 1x equals -50, 1y equals 800, 1z equals 500. So this is a pretty slick way of solving systems using matrices. Next, we're going to take a look at just a couple story problems. I'm going to help you set a couple of them up. As you have questions with the story problems, feel free to send me a message. I have no problem messaging you back, helping you set up your problem, but I will expect that you are able to solve your problems by yourself. If you have issues with solving systems, do make sure that you specify that you have set up your equations that you need. You're just struggling with solving the system. So make sure when you're sending me questions, you're saying whether you're having issues setting up your systems or whether you're having issues solving the system. And always make sure to show me everything that you've done so far. So make sure that if you have your system set up, that you include what systems you have in your message to me, so that if you have an error with your systems, that I can catch it pretty quickly instead of us having to email back and forth a few times before I catch your mistake. Our first story problem that we're going to look at, we have a man that has 20 coins in his pocket, all of which are dimes and quarters. If the total value of his change we happen to know is 335 cents, how many dimes and how many quarters does he have? Well, we know that he only has dimes and quarters in his pockets. I'm going to let D be my variable for dimes and Q be my variable for quarters. And if I added the number of dimes and the number of quarters together, I should have 20 because he has 20 coins in his pocket. Now we have to take into account the total value of his change being 335 cents. Each dime is worth 10 cents. Each quarter is worth 25 cents. So 10 times the number of dimes I have plus 25 times the number of quarters I have will give me 335 cents. Now, you can solve this using any method. It's set up nicely to use elimination, but you could choose to use substitution as well if you wanted to. You should come up with, and go ahead and pause, try to solve it before you look at the solution here, but you should come up with 11 dimes and 9 quarters. All right, one other story problem that is interesting that I'd like you to look at together with me for just learning how to set it up. In any quarter, the college needs to make available 4 less English sections than math sections. In any quarter, student demand for the optional philosophy course is half as many sections as English sections. Available classrooms limit the total sections of all 3 courses to 54. Given these constraints, how many sections of each course should the college make available in each quarter to meet the demand? Well, we're looking for the number of English, the number of math, and the number of philosophy courses. So we have 3 unknowns, so we're going to need 3 equations total. And each bit here gives us an equation to write. The first little bit says in any quarter the college needs to make available 4 less English sections than math sections. So English is going to be a smaller number than math, right? So you're going to take the number of math minus 4 gives you the number of English. So English equals math minus 4. Now, in any quarter, student demand for the optional philosophy course is half as many sections as English sections. So philosophy is half the size of English. So philosophy equals a half times English. Now, available classrooms limit the total sections of all 3 courses to 54. So that means philosophy plus English plus math has to equal 54. This one you can solve with any method. You could try to start out by doing some substitution. You could try to start out by doing elimination. You could even try to do this by using a matrice if you wanted to. Go ahead, take a little time, try to solve this one. You should come up with the solution of 24 math classes, 20 English classes, and 10 philosophy classes. So that's it for Chapter 7. If you have any questions at all, please make sure that you do email me, and I will get back to you with a solution as quickly as I can.